Today we're going to talk about what the algorithms are running on, the system they're running on. So it's not enough to define the algorithm properties because there's many variations on the system, failure variations, synchrony variations, and the algorithms will be very different even with a small change here, okay? And so that's what I'm going to talk about today. The model properties, failure and synchrony, the different kinds of node failures, and we'll start writing code. And we will base the whole course on one kind of network link, which is called a fair loss link. That's all I'm asking from the networking people. They give me this. And the whole course is built on top of this one little thing. Okay, and then we'll define synchrony. And then I'll talk about failure detectors. A failure detector is a black box that tells you when nodes fail. It has some properties, completeness, accuracy. You usually want it to say reasonable things. And there's two main kinds, which is P, perfect, and this symbol here, this diamond symbol, means eventually, that's coming from temporal logic, but I'm not going to say so much about temporal logic. It means eventually perfect. So this is a very important one, because this eventually P is the one that works for partially synchronous systems. So the eventually P is a very important one. Okay. So let me go on now. Okay, and better late than never. Always a few words for the Ukrainians who are fighting for their freedom and for Europe's freedom. Okay, so let me talk about the failure assumptions, different kinds of failure. And there's many different kinds of failure, of course, because the real world is very complicated. Okay? So this failure is part of the model, okay? Failure and timing, so the synchrony. So the failure behavior is part of the model. And of course the real world is a very complicated place, so there's many different kinds of failures, but it seems there are 4 different kinds of failures that are particularly interesting and that people have focused on and written algorithms for. Crash stop, omission, crash recovery, and Byzantine failures. Okay? And this, if during an algorithm a node fails, then we say the node is not correct. So a node that does not fail during the running of the algorithm is called correct. Of course, it may fail later, but we're only interested in what happens during the algorithm. Let me explain the 4. The first one is the easiest one, crash stop. This is very, very simple. I take an axe and I chop that laptop and cut it into 2 pieces. It just stops working immediately. That's a crash stop failure. So the node just stops. No more steps, no more receive, no more send. It just cuts right there and stops, okay? This is very simple, but actually it covers a lot of failures in real life, okay? And this is the default model we're going to use, okay? This will be our default model, the simplest one, and most of the algorithms will use this model. So simple. Look how simple it is. Okay? But I have a question for you. What happens if the battery runs out, this computer crash, and then I reboot it? What happens? Is that a failure? What is the right way to treat that? So you might say, when I reboot this computer, it recovers. It's back. Okay. But in the crash stop failure, there's no recovery. Okay. It's crashed forever. The node disappears forever and never comes back. So how do you model, I want you just to think, how would you handle rebooting computers with this? Would you allow recovery or maybe do a different way? Maybe when the computer reboots, it's considered like a different computer, a new, fresh one. Okay? What do you think? Which is the best way? Well, it's not so easy to know that. You have to write algorithms. The best way actually is that when a node crashes, it truly crashes forever. And when it reboots, it starts fresh. So it's actually a new node. You consider it to be a new node coming into the system, okay? So rebooting computers are part of this model. That's the simplest. The next one is a little bit more complicated. This is network kind of thingies. Omission failures, that it forgets to send a message, or the message disappears or something, okay? Or it forgets to receive. The message comes in, but somehow the algorithm never uses it, it disappears. So the send omission would be an element disappearing from the outpuff without a delivery. Just boom, disappears. Or an element disappearing from the inbuff. This is kind of, in real life, this happens when messages are corrupted in some way, for example, and the system does no checks on or just ignores the message. And sometimes, if there's a lot of like noise and stuff, electromagnetic noise, you can have lots of emissions, okay? So this kind of failure is only on the messages. See, the node keeps working here, but kind of in a funny way, because it doesn't get all the messages and it's not able to send all of them. So this is a funny kind of failure, and I mention it because it actually happens in real life. Here's the third one. The third one is even weirder. This was called crash recovery. This one, the node crashes, but then it recovers. The same node recovers, not like crashed out. The same node comes back after a while, and there's a special in the code, recovery event. So you can actually run a piece of code when it recovers. So it restarts in some initial recovery state, with the recovery event, and it has some stable storage. So the memory, the local memory of the node, there's two kinds. There's memory that disappears when it crashes, and when it recovers, it's gone. And there's memory that survives. So when it recovers, it sees the memory. And that's called stable storage. Okay? So this is a weird kind of failure. The node is running, all of a sudden it crashes, part of the memory disappears, and sometime later it starts running again, and part of the memory has been erased, but the other part has not been erased. And that can happen several times. It's kind of weird. So why would this appear in real life? Where would this appear? So this is not just invented randomly. This kind of thing actually happens a lot. Where does it happen? You tell me. Come on, you guys. Mathieu has told me you guys are very smart. So I want to get the same opinion as him, okay? So and he says you have done very well in the lab session so far. So where would this appear in some practical computing device? Tell me, yeah?
When you have a file, that is a
file, right? On a disk. Yeah, so this is typically the stable storage, exactly. This is the disk storage, okay? This is, if I were to reboot this machine, the RAM disappears, but the SSD storage will stay, okay? So this fits with the crash recovery, okay? And usually the stable storage is considered to be more expensive. It's more costly, but it survives. Okay, so that's the first part. But crash recovery is not so simple because things can still go wrong. So this is normal. Huh? If a node crashes and recovers, that's normal. That's considered correct. It's not actually crashing yet. But a crash recovery node can actually fail. And that's not the same as crashing and recovering. Huh? So for example, what if it crashes and never recovers? Well, then it's really failed, huh? Then it's actually faulty. The node is actually faulty. But there's another way that it can do badly, is when it crashes and recovers infinitely often. So it's always crashing, and a little bit later it crashes again, and then again, and again, and it never stops crashing forever. And recovering, huh? So that's kind of really nasty, and that is also considered a failure. Okay? So the node is considered unstable. So if your disk has that behavior, I mean, if your computer has that kind of a behavior, where it's crashing every 5 minutes, forever and never stops, even though it recovers, it runs a little bit, crashes again, that's not good, and we consider that also to be a failure, okay? So that it keeps, there's something wrong that forces it to crash all the time. The crash recovery should be kind of exceptional, it should not be happening forever. Okay? So a node is correct if it crashes and recovers only a finite number of times. Okay? So that is what is a correct node. So for example, if my system crashes and it reboots, that's not something that happens every 10 minutes. It just happens occasionally, like for example, the battery is exhausted or something. Yeah? And then it reboots and we're good. Okay? And this is good. And the node that does that is considered correct. Okay? So you can say that eventually, and the word eventually means after some finite time, it will eventually not crash anymore. Okay? And after that time, it will keep running and no longer crash. Of course, we do not know what that time is. That's the point. Maybe it's 5 times crash and recover. And then, will it do that a 6th time? Well, maybe, or maybe not. All we know it's finite. Okay? So we don't know how many times. All we know, when we reason about the algorithm, is that there's a finite number of times, that after a certain number, it won't be a problem anymore. Okay? So this is typically for databases. Cosmic ray goes into the RAM, flips a bit, parity error, the system crashes, recovers. Fine, that's something that happens extremely infrequently, and many algorithms can run between 2 cosmic rays. Okay? So that's okay. But if there is lots of sand in the disk, dust got in there, which is very nasty. So the disk is rotating, and the dust is kind of causing all kinds of marks on the magnetic layer. Well, that's not good, and probably it will never stop crashing and recovering. Okay? Okay, for that. Final one is Byzantine. This is the most general one. The node is behaving totally arbitrarily. It can be running different code. It can be running enemy code. There can be code in there that is designed specifically to break the algorithm. So the algorithm that we design has nothing to do with actually running. It may behave maliciously. It can be arbitrarily smart. Okay? It can send and receive messages as long as, I mean, it's not going to use telepathy. Yeah? As long as it obeys the laws of physics and runs something, it can be arbitrarily smart. That means 2 of these nodes may work together. This is called collusion, to break the system up. So if you have n nodes and some of them are Byzantine, that's a problem. Okay? And the internet, which is a very open system, that can be a problem, especially when you use the internet for things when money, for example, is involved, or real-world actions are involved. You can have this kind of thing. Of course, these algorithms they exist, but they're very complex and very slow. So it's possible to protect against these kind of errors, but with very complex algorithms. Okay? So usually you don't want to use it. If you can, you avoid them. So usually what you want to do is create an area where that only good guys can walk in. There's a kind of border guard, and once you're inside, you can communicate freely without doing Byzantine. Then it's efficient. But that's not possible, like in a cryptocurrency, where you have many players on the open internet, then you need this kind of algorithm. Okay? So you try to avoid it, but sometimes you can't. Okay. So I explained then these 4 algorithms, the 4 types of failures, but there's a hierarchy. So they're actually subsets. One kind of failure is a subset of another one. One is a special case. So for example, crash stop is a special case of omission. If at a certain point in time we omit all receives and sends, then it's totally indistinguishable from crash stop. Okay? So a crash stop is a kind of omission. Okay? Is a special case of omission. But omission is more general. Omission, you can have a few messages dropped and then it keeps going again. Crash stop, once it stops forever, it's stopped forever. What about crash recovery? Okay, now we can reason. We can actually connect crash recovery to omission failures. Okay, so let's do it in 2 steps. So I want to make some connection between crash recovery and omission. So let's say I'm using a special case of crash recovery where I only have stable storage, no RAM, only disk. Okay? And when I do that, crash recovery is identical to omission. Okay, when it crashes, eventually it recovers and the memory will be back, okay, the stable storage. It's exactly the same as if the send and the receives were omitted while the node is crashed, okay? When it crashes, it's like the omissions start right then, and when it's recovered, then it starts receiving messages again, okay, sending again. So it's like, exactly like a crash during this period, okay? So, crash recovery with only stable storage is a kind of omission, okay? Okay, so that's one thing. But crash recovery is more than that. Crash recovery also has RAM memory, volatile memory, which disappears when it crashes. That means when the node recovers, it can't recover all the state. It forgets something, some kind of amnesia. So when the node recovers, it has forgotten some stuff, which doesn't happen in omission. Okay? So you see that? So this is not happening in omission. So omission is a special case of crash recovery. Crash recovery is more general because of the amnesia. Okay? Omission does not have amnesia. Okay, so this is a little bit more subtle. And the final one, of course, everything is, crash recovery is a special case of Byzantine, because everything is a special case of Byzantine. So here's a diagram. So each little ellipse is a set of possible failures, and you can see there's strict subset. Crash recovery is a special case of omission, crash is a special case of omission, special case of crash recovery, which is special case of Byzantine. That means if we have an algorithm that can survive crash recovery, it will also survive omission and crash stop. Okay? If we have an algorithm that survives Byzantine failures, it will survive all the others. Okay? Okay, so that's simple, right? This being said, most of the course we will talk about crash stop. A little bit the others. There's a huge amount of literature on all of these. But by far the most important ones, well, crash stop is very important. Crash recovery is important for disk. But if you're writing disk algorithms, and Byzantine, of course, is important if you're in an extremely hostile environment. Okay? Okay, that's the first piece, the failure assumptions for the nodes. Now let's talk about the network. Okay? The network, the channels. So now we're going to start writing code. And I'm going to write code, and the code is based on, let me get this chalk. It is based on the fair loss link. This is the foundation. So we assume a fair loss link. Okay, a fair loss link is a connection where you can send a message and the message arrives at some destination, so it's point to point, with some non-zero probability. There's some chance that the message arrives, or maybe it doesn't arrive, but the probability is non-zero. Okay, so there's some reasonable chance. So we will define this precisely in a few minutes. This is just an illustration. This is all that we assume from the network. Okay, and we will build all the algorithms of this course, most of them, will be built only using that. That's the only thing we assume. It's amazing, huh? Huge, we're going to build this huge edifice on top of this one little stone, which is the fair loss link. Okay? And all that we ask from networking people, like Mr. Olivier Bonaventure, my eminent colleague, is that he provides us with this thing. And all kinds of optimizations here, and there's people working hard to make this, but all I'm assuming is that. Okay? Of course, you can talk about other things like performance, bandwidth, latency, and so on, but here we're not going to talk so much about performance and latency. Those are orthogonal properties. We're going to talk about correctness of the algorithm first, and then performance. And I'm going to start writing some code here. So this is given, fair loss. And what I want to get to is perfect link. So I don't like that messages can be dropped. So I'm going to write the code that guarantees the message will be sent, will be delivered exactly once. So I'm going to write code for this. I'm using the event model. So we're going to write some code today. And to make it simple, I introduce this middle layer called stubborn links. When I send a message, it arrives infinitely many times. That's very weird, huh? I send a message and it just keeps arriving forever. Okay? Why am I introducing this middle layer? This is the principle of our approach. Each layer is very simple. We will see the correctness of each of these layers will be so simple it's basically obvious. Okay? So I don't want to compress it all and put the code into one thing. Of course, then you can always optimize that. A real system doesn't necessarily need these stubborn links. Okay? So it's like this. This is the fair loss link. I have a node PI, a node PJ. I have a message. So this is the kind of notation. This is like a record. Huh? I send message M to node PJ. And here on the other side, so the blue side here, I deliver. So basically, deliver means the message arrives and it's sent to the application. So there is a request and an indication in the notation we used. Okay? And here the deliver record tells me where the message came from, PI, and it's the same message. This record, M is an arbitrary data structure. I'm not going to make any assumption on how we represent it. We will just assume that we can represent whatever we need. Okay? So that's the fair loss link. And I will make a formal definition of this. So this is a module. There are two events, a request and an indication. Remember, the request goes down and the indication comes up. Huh? And this is like a record. Huh? FL P2P send is like the label, it's the type, and these are the arguments. Huh? FL P2P deliver. The source, so its destination identifies the destination node, source identifies the source node in whatever form you want, okay? We're not going to make any assumption, and M is the message, okay? So that's the API. It's clear? It's not so hard. And there's three properties, though. The properties are what makes it interesting. So here are properties. There's three properties that we are going to assume that Mr. Bonaventure has to give us. And the whole course is built on top of these three little properties. So FL1 is the fair loss property. If M is sent infinitely often by PI to PJ, and neither of the nodes crash, then it will be delivered infinitely often. It's an interesting way of formulating that. That means you can lose an arbitrary number of messages as long as that's a finite sequence. Eventually it has to come through. If I keep sending forever, then messages will eventually have to arrive because they will be infinitely often being delivered. Okay, that's fair loss, but that's not enough. You need more properties. Notice this is an if. Okay, that means, well, we'll see what it means. Okay, the second one is finite duplication. If a message is sent a finite number of times, then it is delivered a finite number of times. So that's kind of an opposite property. The network is not going to duplicate messages forever. A message cannot be duplicated infinitely many times. So if I send a message once, it might arrive twice, or 0 times, or 5 times, but not an infinite number of times. Okay? If I send a finite number, it arrives a finite number. Notice it doesn't have to be the same number. And this is actually consistent with internet, with IP, for example. Because of routing, it's possible when you send a packet that it arrives twice. Theoretically, it could even arrive more than twice, as many times, depending on what happens to the routers in the way. So this is the way we formalize it. And the final one is important, no creation. We only don't deliver a message unless it was sent. So the network cannot invent messages. So if I don't send anything, the network can't just arbitrarily create random things and send them, okay? The network is not creating messages, so it's an empty network. It's not creating. And then there's these two conditions on the number, okay? Okay? Now, my question for you is, which one of these properties is safety and which one is liveness? Okay, so this is a question that you should always ask yourself. It's very important to specify in terms of safety of liveness. That makes a very clean specification. Fair loss, what is that? Is it a safety or liveness property? And this will always be possible. I'm never going to combine them. So it's always going to be one or the other in these very nice, clean specifications. Fair loss, is it safety or liveness? What do you think? Yeah?
Liveness.
Liveness, okay. Why is it liveness?
Because it deliver it infinitely.
Deliver infinitely?
Yeah.
Yeah, that's right. It's deliver infinitely. But why is that liveness?
Liveness.
Liveness, well, you can give the intuition.
Good things finally happen.
Will finally happen. That means the good thing is the delivery. Yeah. Right, so it is a liveness. You're correct, and it's a good intuition. That means that when you have a prefix, maybe nothing is delivered, but you can always extend it so that it will be delivered, because it has to be delivered infinitely often. So this is a liveness property, okay? What about finite duplication? Safety or liveness?
Liveness.
Okay, who said that? Explain. Liveness.
Isn't it like the same as the previous one?
It's not the same. No, otherwise there would only be one property. I mean, yeah, but it's the same in the sense that they're both live, is what you're saying. Why is it live?
That's the explanation, I mean.
And the explanation is the same. That means that it's delivered a finite number of times. That means when you make the extension, you just have to make sure that the extension does not deliver an infinite number of times, basically. Also, you can only break this after infinite time. So safety can be broken in a finite time, like dropping an egg, but liveness is infinite. So duplicate infinitely often, cannot be duplicated infinitely often, is So the good thing is that it's only finite, and this good thing will eventually happen. Okay. So this is liveness. Yeah. What about this one? So it has to be. We need both, of course. So if these are both liveness, and if we want a nice specification, you need both, of course. So you can say, well, this one has to be safety. But why would this one be safety? Yeah?
Because we do have messages that does not created by content.
Sorry? Say
Like
again.
it's a messages is created is not like self-create messages.
Creating a message is like breaking the system. Once you create a random message, then you've broken this property. Okay, yeah. So that can be done in finite time. So this is a safety because you can break this property finitely. Okay, so that's safety. Okay, so that's good. So you see the kind of this has to be second nature, right? So now I'm going to write some code. But I want to define this middle layer first, which is the stubborn links. The fair loss links will arrive with some non-zero probability, but the stubborn links, they will keep arriving infinitely. So here is the interface again. So here we have a stubborn point-to-point send. Again, you have two records, destination message. I request the transmission and I deliver. And I have two properties here, SL1 and SL2. Stubborn delivery. If a node sends a message to a correct node, and PI, the node sender, does not crash, then it delivers an infinite number of times. And then there's the node creation, which is similar to node creation in the fair loss. Okay? So it's pretty straightforward what these are, right? We have a safety, a liveness, and a safety property. But now we write some code. Okay? So the idea, first to give kind of the intuition and then we'll give the code. It's very simple. So we're going to use fair loss. When I send, I store the message in a local variable, collecting all the sent messages, and then I have a periodic loop that runs forever, and will periodically resend all the messages that are in the sent set. Okay? And this guarantees to satisfy the property if the fair loss is correct. Okay? If the node doesn't crash, it will be sent infinitely many times. And because of the fair loss property, it will be delivered infinite number of times. The lossy fair loss can only drop a fraction. It's not allowed to drop everything, because otherwise it wouldn't be fair loss. Okay? And the node creation is exactly the same property. So it continues to hold. Okay? You can also define it in the formal model. This is just for information. If we have an execution, configuration event. Basically, if a message is in an out buff, we can define a new kind of deliver event which delivers, but without removing the message from the out buff. So it keeps delivering forever. So we could update the model. Okay. But here's the code. And the code is 2 pages, very simple code. So I'm implementing stubborn links, I'm using fair loss links, I have local variables. So I'm not going to declare them, and there's always an init event happening first. The sent variable is set to empty set, so this is going to be a set. And I start a timer, so I'm assuming there are timer and I can have timeout events. When I have a timeout event, so that's upon event timeout, then this code can be executed, and what it does is for all pairs, so we're assuming that the sent set has pairs of destination and message. For all m element of set, I do a trigger, fair loss point-to-point send dest m. So the trigger is a sender, it's a terminology, and then I start again the timer. So this is an infinite loop. So using a timed loop. Okay? You see, I'm actually, if I need data type, I'm just assuming it exists. So send is a set. The set has pairs. I'm assuming I have for all. So I'm not going to spend a lot of time defining the operations and the data structures. It'll be all the obvious ones, okay? There's nothing special. The important thing is we have these separate rules and that the whole thing is single-threaded. And we have two more and then it's done. So when I when I want to do a stubborn send, all I do is add this pair to the send set. I'm just doing a local computation actually, nothing sent. And when I do a deliver, fair loss deliver, then I do a stubborn deliver. So you can see it like this. You can see it as a layered structure. So we have the fair loss and the stubborn link. So they're like this. So this is running on a node, and this is another node. Okay. So these two are communicating. Stubborn. So we see we have now two layered system. If I stubborn send here, it's adding to the send. But if you look at the previous slide, periodically, I'm taking all the messages and sent and doing a fair loss. Okay? So you see what's happening now? When I do this, I add it to the sent variable, and then I have this periodic loop that sends them all. Some of them will arrive here, and when they arrive, they're just propagated back up. That's it. So this is a typical example of the code we will write. So when I get a fair loss deliver coming from the bottom, it's just propagated upwards. Okay, you see that? The fair loss point here is just propagated. And that's it. Okay? This is the first real code that we've written. So you see this is not so hard, right? It's easy to understand. So you understand this, So these four rules together are running in a single yellow box, as we showed, and it's single-threaded. That means only one rule can be running at any time. And whenever an event happens, so there's an it, timeout, and then there's these two events when messages are received, then a rule can be executed. So it's possible that there might be two events, two rules could be executed. Well, the system will choose one arbitrarily, execute it, and then the other one. Whenever an event arrives, all we know is that eventually the rule will be executed, and that's it. And the whole thing is single-threaded now. You see how it works? This gives us the stubborn links. We make the next step now to perfect links. Perfect link is the top layer. So we have a send and a deliver, just like before. And we have three properties. Just like before, we have just some properties. Okay. Reliable delivery. Here we're not talking about infinite anymore. If neither PI nor PJ crashes, every message sent is eventually delivered. Yeah, that's it. At least once. But then there's our second rule, at most once. Okay, so this is at least once, at most once. And then there's the no creation. So at least once, at most once, and the network does not create messages. So all three of those together give you a perfect communication link. Okay? And you can figure out which of them are safety and liveness. So at least once, PL1 is liveness, at most once is safety, and the no duplication is also safety. So again, we have safety and they're both safety links. Okay? Okay, so this one will be built on top of the stubborn links. So we're going to add another layer on top here. A third layer. The perfect links. Perfect perfect point-to-point. So we have now our system of 3 layers. This one is going to use the stubborn links, and it uses another data structure. So again, it's going to be very simple. It keeps a log. So the stubborn link kept a set of sent messages. Well, the perfect link will keep a log of delivered messages. And when it receives a message, it will check whether it's in the log that was already delivered before, and it will only deliver messages that were not delivered before. That's very easy, yeah? And you can prove that it's correct. So it's reliable. That means it will be delivered at least once. Well, that's guaranteed by the stubborn link, of course, because the stubborn link will deliver it infinite. So infinite is clearly at least once, okay? No duplication. The log will guarantee that. We only deliver a message if it was not delivered before. And no creation. So this is guaranteed by the stubborn link. We have to reason a little bit about the sent set and what's in there. But what's in there is only things that were put in by a send. There's no local computation that adds weird stuff in there, okay? So you have to reason a little bit about the send link. That's why there's a little E. So you should think about that. Look at the code. Huh? Okay, so we're going to write the code. This code is very easy. It fits on one page, one slide. Perfect links uses stubborn links. There's the init event. So here we have the log, which is a delivered set. When we do a perfect send, we will do a stubborn send, so it just goes down. When we do a stubborn deliver, so the indication coming up, we check whether M is in the delivered set. If it's not, then we put it in there, and we propagate this send up. So trigger is a send. So event, the SP2P is the message received from below coming up, and this one goes further up. So you see the messages here. The messages are going down. Here they're going up, and the code is in the middle. There we go. That's it. Now we have a beautiful 3-layer system, and the proof of correctness is very simple. Okay. Okay. So for the course, we will usually use perfect links. Okay. We only actually expect the network to give us this fair loss, but we usually will assume that the links are perfect when we write our algorithms. Otherwise, the algorithms are too complicated. Okay. We will also assume that messages are unique. That when I ever send a message, it's a unique message. So if I send the same data structure twice, I consider that as 2 separate messages, okay? So I'm usually assuming that the messages are going to be unique. That's usually what we need to do. In a packet, for example, there is usually data added to guarantee that. If I send a sequence of bytes, and I'm sending the same byte twice, well, it will be sent with different messages. There will be sequence numbers added. So this is the usual assumption. All messages are unique. Okay. Final point, stubborn links are not as useless as you might think. They can actually be used in crash recovery. Okay. So a little bit of discussion. So this is what I just showed you is a very abstract thing, this perfect point links. But in practice, we have this thing called TCP, Transition Control Protocol, so which kind of does some of this. So TCP, for example, will send messages and will, if a message does not arrive after a certain time, so a packet, it will request that the packet be sent again, okay? And so it also has to remove duplicates. So how does it, you remember how TCP works? You've seen TCP, right? So you have some intuition. So how does TCP work? It has an optimization. It doesn't actually keep all the messages in a set. It has something else. It optimizes by doing what? So it optimizes. And here we have the full sets, not efficient, especially they're always growing. Well, TCP also has something that's always growing, but it's not a problem. Why is that? I'm being very cryptic because you should know it. So what is growing in TCP? Come on, you guys. When I send packets in TCP, there's this windowing thing. So what does it mean? There's an order. Sorry? Sequence number, yes. So the TCP numbers them in a sequence number, and it represents, so as a window of the packets that are received. So this actually represents the set of received messages. And when the whole thing is full, the window moves, so it slides. It's called the sliding window. Okay? So it's using sequence number. Okay? And so the window, you have multiple packets that are in flight. And the reason why you have multiple packets is that will improve performance. But not too many or you have congestion. So there's like a sweet spot and so on. So TCP has a lot of optimizations that we are not going to talk about in this course. Okay? So I mentioned TCP just to make the difference. So TCP could be seen as an optimized version of this kind of perfect point-to-point link. But we're not going to talk so much about these very low-level optimizations. Okay? It's very easy to add them to represent these things efficiently, but that's not the point of this course. This course, we will be, we will have other cats to whip, although I don't like whipping cats or whatever, other bad guys to punish, which means we are worried about concurrency, distribution, failure. So it's already complicated enough. Okay? So we're not going to worry about these low-level optimizations. Of course, practical network protocols are invented by basically crazy guys who love optimizing and who don't care if things are very complicated because they love complexity. That's their bread and breakfast and bread and butter. All in the name of performance, latency, throughput. So we're not going to worry about that. We have other bad guys to go to capture. Okay? Okay, so that's the discussion on failure assumptions here and fair loss. So you can see the kind of the world we're living in, okay, and what we are based on, and the kind of thing we want to show. And we actually abstractly want to go very far, so we don't want to be slowed down by all these low-level optimizations. You can always add them, of course. All the practical systems will add them. But the main thing, okay, so this was a professor of mine who said, was, the biggest gain in performance comes when your system makes the step from not working to working, okay? And that's what we're worried about here. The further optimization is not really a subject of this course, okay? Okay, so let me make a small break. There will be a course tomorrow during the lab session. So this is because I was ill last week and could not give the course. So the course will be given tomorrow during the lab. And it's Mathieu who will be giving it. And he will talk about reliable broadcast. So he's going to start writing lots of code. So I started it here, but he will continue that. And reliable broadcast is one of the real fundamental important algorithms. And it gives real strong properties. So Mathieu will explain that. And also a version called uniform reliable. And this has to do with failure. And it's a little bit subtle. It's an even stronger one than the normal reliable because it's better, has a better failure behavior. But the algorithm is much more complicated because of this small improvement. So you'll see how that works. Okay, so that's tomorrow. Another thing is that I gave this paradox of time complexity as an exercise. So I expect that some of you have thought about that. So I'm going to give you some hints on that. So I have this network with some source node. So let me just make a small diagram here of the network. Okay. And then there's another nodes coming out here. So let's say we have here, we have n nodes. Here we have n over 4. And here we have 3n over 4. And now we have the two cases. Remember, we have the A messages and the B messages. Okay? I think it was the A going down and the B coming up. And then there was the two models, where A can be 0 or 1, and the model where it's always 1. So if the time is always 1, how long does it take for the messages to go all the way down and back up? So you can figure that out. If the time could be 0 or 1, assume now that this chain will make the messages go at time 0, when we go down. But when they go up, they have to go back slowly. So if in those two cases you calculate the up and the down times, you will see that if you allow this fast messages, that the algorithm will slow down. Okay? That's enough hints, I think. You can work out the rest yourself. So you see, it's very easy to find networks that where things slow down if you allow fast messages in the algorithm. Okay? Because you have more possible executions. So they cannot get faster, but they can actually become strictly slower. Okay? Is that good? Does that make you happy? Satisfied? I can say more, but I expect you from that to be able to work it out. Huh? Okay, so let's talk about synchrony now. Something that we've already talked about a bit. So we're talking about speed now, but not speed in terms of clock time. Speed in terms of eventually things happening, finite or infinite time. See, it's an abstract form. Again, we're not worried about the precise performance. We're worried about correctness. Okay? So we have the node speed, the channel speed, and we can see there are three kinds of systems. The asynchronous, synchronous, and partially synchronous. So I will review them, but I will spend more time on the partially synchronous, which is kind of the most important one. The asynchronous is the most relaxed one with the least assumptions. No timing assumptions. Processing time can be arbitrary as long as it's finite. Transmission time can be arbitrary as long as it's finite. Okay? And the formal model is, this is what it models. The formal model models causality. It's just connecting events, but it's not telling us how much time is passing. Okay? All that we know is that it's finite. Okay? And you can't actually see the wall clock from this form model. If you only have this kind of assumption, you can see that you can't, with no wall clocks, then there's no other way. With causality, you cannot see the actual total order because we're only worried about finite or infinite. Okay? So that's the most relaxed system. When I send a message, it arrives in some finite time, or if there's a failure, it will never arrive. Okay? If I do a computation, then it will take some finite time. And then the question is the internet asynchronous? And we already discussed this a little bit. So, in some sense, the internet is asynchronous, because there's no time bounds built in to the routing protocols of the internet. Okay, it's basically a system, a best effort system, and it depends on the distance, depends on the speed of the routers, depends on the performance of the network, the cables, protocols, whatever. So there's no bounds built in to that. Okay? So you might say, yes, it's asynchronous. But that's a very nasty, because that makes, if it would truly be asynchronous, that would make things very hard and impossible. Okay? So we have to see whether we can think a little bit more and understand better the internet. Okay, the other side is synchronous systems. Now these are the strictest form of distributed system. You have all the nodes that are computing in lockstep. They all take the same time, basically the same upper bound. So they're all going one step forward at the same time. And the message transmission is basically always the same. Basically, there's a known upper bound. Every node can send a message to any other node in this one time step. Okay? And all the nodes have a physical clock, and all these physical clocks are counting exactly in the same way. So in practice, for the real hardware clocks, we know the clock drift, okay? In terms of nanosecond and so on, we know exactly how these clocks relate. But the steps of the synchrony are perfectly synchronized. So this is a very strong kind of connection between the nodes. It's not easy to build a system that does that. So why do we study these systems? What do you think? Because, I mean, maybe they're not practical. The internet is not like this. What's the reason to study these systems? There's actually many reasons. Why do you want to understand this kind of system? Well, there's theoretical reason and practical reason to study them. So there's a practical reason. You tell me. There's a practical reason. I'm looking at it here. So these small, very small processors are very good close approximation to a synchronous system because the distance is so small. It runs at some number of gigahertz and it's very synchronous. And the communication time between the cores is very well understood, very well measured and known. And it's just a few cycles. So these are basically synchronous. So small systems, physically small systems, can be made synchronous. And so that's one reason. So we have these systems do exist. Okay? But once you have larger systems, they're not synchronous. But small, physically small systems, also clusters with high-performance backplane can be considered as synchronous. Okay? So that's one reason. There's also theoretical reason to study this, because it's kind of an extreme case. The algorithms on this are the simplest, because the system has the strongest assumptions, so that makes the algorithms very easy. Failure detection is very easy here. Okay? The message doesn't derive in the time of the bound, you know that something has failed for sure. Okay? So failure detection is very easy, and many algorithms like consensus are very easy in this kind of a system. So algorithms are very easy, and they do exist, such systems. Okay, so that's why they're important. But in real large-scale distributed systems, of course, the systems will not be synchronous, and they tend to be more asynchronous. But asynchronous systems are very hard to program. So in the 1990s, people were scratching their heads, and it was mostly Leslie Lamford who was scratching his head and came up with an answer, is that the internet is not actually truly asynchronous. This is actually a better description. It starts being asynchronous. That means when you start running your program, you don't know what the message time is, but eventually there will be a bound. That's kind of a very vague thing to say. It means I'm running my algorithm on some nodes that are maybe close together, and so there is some bounds because they're all sitting in a room, for example. I just don't know it. But eventually, I will see that that the messages are always within that bound. And because they're running inside a room, the bound will be strict and hold. Okay? But that's not always the case. Maybe when I run my algorithm, sometimes it has to go outside of the room and talk to someone far away. That breaks the bound, but it's actually running in a bigger space then. So eventually, there will be some space in which the algorithm will be inside of that space. And that means there is a bound. Okay? It might be the whole Earth, but the whole Earth is a finite space. So it will be a bound. Usually it's much smaller than the whole Earth. Okay? So how do you formalize that? Because you don't know any of these bounds. You don't know the numbers. I mean, yeah, you can measure them, but in this course we're looking at correctness. So all we know is something kind of vague. The system starts, when it starts running, it's asynchronous. It means you don't know, there's no bounds. But eventually there's bounds, because you realize you're running in a room. And but you don't know when that you will know that. All you know is that you will, at some point, there will be bounds, and you don't even know the values of the bounds. You only know they exist. Okay? So eventually, there will be some bounds. That's all you know. You can see it's kind of an exercise in vagueness, huh? But there's an intuition there. So your algorithm takes some time to run. So in some time window it runs, but in this window it's running in a certain space. So that you can say it's actually behaving nicely in this time window. That means nice means it's synchronous, and so that it can achieve its goal. And so that you can assume that there are bounds. Okay? So are there such systems? Well, yes, luckily there are. Okay? So if you look at the internet, it's basically a system like that. Because it's basically a nested set of networks, and each bigger one has larger time bounds. So if you run your algorithm, eventually it will find the largest network that it's running in, and at that point you will have a bound. When will that happen? You don't know exactly when it will happen, but you know it will happen. Okay, at that point we will have a bound. So the internet is such a system. This was a major kind of discovery, okay, because without this property we would not be able to run practical distributed systems. Okay, so as you know, I like doing thinking visually. So here's one way of visually. So your algorithm starts running, so this is the time. So here it's asynchronous, that means you don't know that there's no bounds. But at this point, there are bounds, okay? There will be bounds, but you don't know them. And at this point, from this point onwards, your algorithm is actually running on a synchronous system, okay? And because of that, it will eventually terminate. That means you don't have the whole disadvantage of the asynchrony. You're actually running a synchronous system. The point is, you don't know when this will happen. You just know that somewhere it will happen. And you don't know what the bounds are. You know that there are bounds. One way for me that I like to visualize it is a boat on the ocean. So the boat is traveling across the Atlantic, okay? It's discovering the new world, and there's a storm. So if everything is calm, then we're here, and it reaches the goal. But if there's a storm, then we don't know anything, then we're here. So basically the algorithm has to make sure it doesn't do stupid things here, that it will wait long enough until it's here before actually making a decision. So if you run a consensus algorithm, you cannot do any decision until here. The algorithm has to make sure it's here before it actually decides. And it can do that, okay? So that's important. So that's an important concept for this course, okay? And so we'll be using it very, very often. Okay. So that's one of the three main discoveries, or inventions actually, that made distributed systems into a clean and nice discipline. So the event-based layered model for writing the code, the partially synchronous assumption, very important, and the third one is failure detectors. With this, the code becomes very, very simple. So failure detectors, we can use it also when writing code for partially synchronous systems. Okay? Okay, so now let's go back into the past, in the 1990s. In the 1990s, when you write distributed algorithms, over and over again, you have to model partial synchrony, timing assumptions in the algorithm. So this made the algorithms very complicated. And at some point, there were some guys that said, no, we don't want this complexity. And they invented this concept of a failure detector. And all the timing stuff is inside. So it's like a box and lots of ugly stuff inside, but the code outside is much simpler. So it's a black box that tells you things, but it tells you suspicions. It doesn't always give you the right answer. Okay? And this was invented in the early 90s. So this was one of the main inventions that made distributed algorithms much easier, especially for partially synchronous. Okay, so let me give you make it more concrete. So this is the yellow box, like we did in our model. So there's code inside here, and there's messages coming out. Okay, so this is a failure detector, and this one is called P, means perfect, and there's only one kind of message coming out, crash PI. So if it sends the message crash PI, that means it's telling you node PI has crashed. And it's guaranteed to be always right. Never makes mistakes, this guy. So this guy is like, this is the one we want, okay? It tells me P1 has crashed. Yeah, that's it, P1 has crashed. So P2 has a failure detector telling me crash P1, okay? So this is the P failure detector. But there's some magic code running inside this box, huh? But it turns out you can only make this one on a synchronous system. You can't implement it on a partially synchronous system. So there's another failure detector, which is not as smart, called eventually P. So the little diamond means eventually perfect. This one is implemented on a partially synchronous system. This one has two kinds of messages coming out. Suspect and restore. So P1, I suspect P2 has crashed. So just suspect. But maybe that's a mistake. So later on, it will do restore. It says, no, that was a mistake. Restore P1. P1 has not really crashed. So this one is allowed to make mistakes. So it can suspect a node, but it can correct the mistake. Okay? But eventually, it stops making mistakes. Eventually, so after some time, it will be always right. So that's nice, huh? The problem is we don't know when. So when it tells us something, maybe it's still a mistake, but maybe it's already in the time when there's no more mistakes. We don't know when. That's a very interesting abstraction, huh? But that's exactly how it works. So this is what a partially synchronous system gives us. Okay? It gives us an eventually perfect failure detector. Okay? So how do we implement these things? Well, it's not that much, it's not so much rocket science. They do heartbeat messages. So these boxes will send messages regularly, like they will ping the nodes, and they will measure the round trip time, and they will see if there's a timeout. I don't get a ping within this amount of time, and so I suspect the node. Okay? But then maybe it's just slow, and I get the ping eventually, and then I will revise my suspicion and increase the timeout. You see? So the timeout is like an adaptive thing. So this is typically how it's implemented. But of course it can be smarter too. Huh? Okay. So these failure detector thingies, we have to specify them. We have to make specification of them. And there's two kinds of specifications. There's what's called completeness and what's called accuracy. So there's two kinds of properties, and this is very closely related to safety and liveness, as you will see. Okay? So completeness means that they don't miss a failed node. So they actually see, when there's a node crashed, they see it, and they don't miss it. Okay? So they're complete, they see completely all the nodes. So the completeness means they see all the crashed nodes. They actually see them, the failure detector. They don't miss one. But accuracy is regarding mistakes. So if there's a node that's alive and it's telling me it's crashed, that's a mistake. That's not accurate. Okay? So the accuracy is that it's not actually making a mistake on a live node, telling me that one has crashed. So it's like you basically want both, you see. Yeah? I want to see all the crash nodes, but I don't want to make any mistakes. So there's these two properties, completeness and accuracy. Okay? Of course, like safety and liveness, they're very trivial to achieve if you only want to do one of the two. So if I only want completeness, what's the easiest way? I don't care about mistakes. I just want to make sure I don't miss any crash nodes. What's the easiest way to do that?
Although that's crashed.
Yeah, just say that all nodes have crashed. Of course, that's kind of stupid, but you won't miss any. And the same for accuracy. How can you be completely accurate and never inaccurately suspect a live node? It's very easy. You just want to do this. Just say what?
It's not suspect.
Say all the nodes, are not suspected or alive. Just say that none of the nodes are suspected. They're all alive. So that means I will never make a mistake for a really alive node and say that it's crashed. Of course, the trick is you want both at the same time. Okay? That's always the trick. Huh? You want both at the same time. Okay, so a failure detector can actually be added to the formal model. So we're not going to worry so much about that. You can implement it, but you can also add it to the formal model, where you have the FD state, the failure detector state of a node, okay? And there's some function, and it satisfies some properties with respect to nodes, okay? Now, there's actually different kinds of completeness and accuracy. In real systems, there's a difference between strong completeness and weak completeness. So strong completeness is that if there's a node that crashes, all the nodes will see it. All of them. That's strong completeness. There exists a time all crash nodes are detected by all correct nodes. So all correct nodes will see all crash nodes. Okay, but that's not always the case. Okay, but this is the case we're going to mostly look at. But just to say what another possibility, every crash node is eventually detected by some correct node. That means there is some node that is somehow privileged. It sees all the others, and if there's a node that crashes, it sees that. But the nodes, many of the nodes won't see it. So the analogy is, if I have a football stadium with 100,000 spectators, and I have the players there, okay? So if one of those spectators falls asleep, how dare he fall asleep during the game, the players can see that. The players can see all the spectators. Because the spectators can see the players. That's the thing. Players can see all the spectators, but the spectators cannot see each other. So the privileged nodes here are the players, and they can see whether or not a spectator has fallen asleep. So that's a typical example of weak correctness, okay? Weak completeness. And then accuracy, there's also a strong and weak version. So the strong version is very simple. No correct node is ever suspected by anybody. That means if there's a node that's correct here, nobody will ever suspect it. That's perfect. Huh? Nobody will ever make a mistake. Okay? But is this realistic? So this is very hard. This is very hard to do, actually. It means no timeouts anywhere. No premature timeouts with respect to anybody. That means everybody will get the messages from that node and nobody will ever have a delay. That's a pretty strong assumption. Okay, so that's kind of a strong property. Okay, but there's also a weak accuracy, a weak version. Okay, there is at least one correct node which is not suspected. Nobody will suspect it. Okay, so again, I like the football analogy. Okay, so here it's the opposite. So the players on the field, everybody can see them. So as long as they're running around, nobody will suspect that they're actually sleeping. Okay, all the spectators will see that they're not asleep. Okay, so the players are satisfying weak accuracy. Okay, and there's more properties. Okay, but eventually we will narrow it down. I just want to explain to you kind of the different possibilities. There's all these properties are eventual also, eventual strong accuracy. That means I'm allowed to make mistakes. I'm allowed to make mistakes, but after some time, I won't anymore. Okay, so that's kind of going in the direction of partial synchrony. Yeah? And the same for eventual weak accuracy. I'm allowed to make mistakes, but eventually I won't make mistakes with respect to some of the nodes. Okay? Okay? So these assumptions are more like for partially synchronous systems. Okay? So let me explain, but don't worry. So I'm going to show you a whole pile of possible failure detectors, but in practice we will only be using 2 of them. Okay? But it's important because people sometimes talk about these other ones. So here are 4 detectors with strong completeness. So the best one is called P. This is a standard name. It's also strongly accurate. That means it sees all the crashes and it never makes a mistake. That's perfect, okay? This is the perfect one. But there's also the strong detector. So it sees all the crashes, but there's only one node that doesn't make mistakes, okay? It's weakly accurate. And then there's the eventual versions. Eventually perfect and eventually strong. So why is this one called strong when it's weak? Okay, beats me. That's a historical accident. Okay, because the perfect one is stronger than the strong. Okay, so the strong detector is actually weakly accurate. Huh? So sorry about that. That's a historical thing. But we won't be talking so much about this one. The partially synchronous system. Remember, it starts being asynchronous. Eventually, there's bounds. That means the failure detector is not perfect, but it's eventually perfect. That means it starts out making mistakes, but after some time, it doesn't make any mistakes anymore. This is the one, eventually P. This is the one that's called eventually P that we'll be using the most. So by far, the 2 most important ones are T and eventually P. Okay? And then there's even other ones, which I will just present, which we'll basically never use, but because, to be complete, sometimes if you look at old papers, they will talk about these. You have also detectors with weak completeness. That means only the privileged nodes will see the crashes. So you have the detector Q, which is called Q, strongly accurate, and the weak detector, which is weakly accurate, and you have eventually Q and eventually weak. Okay, so this is for partially simple. So these are 4 other failure detectors, but they're not used so much. Okay? But let me now explain to you how to implement them. I will show you the interface, I will show you the properties, and we write the code. And I will show you the 2 most interesting ones, P and eventually P. Okay? So I'll start with the easy one, perfection, the perfect failure detector. So the interface is very easy. There's only one indication. So if there's a message coming out, request indication. Going up, crash PI. That's it. So it just sends you messages. Okay? And it has 2 properties, which are strong completeness and strong accuracy. Okay? Eventually, every node that crashes is permanently detected by every correct node. That means if a node crashes, I will see that, but not instantaneously. A little bit later, because of course it takes some time, I will see that, but I will always see it. And if I think a node has crashed, then it has truly crashed. No mistake. So again, these are safety and liveness. So up to you, as an exercise, to tell me which one is safety and which one is liveness. Okay? Exercise for you. But unfortunately, the slide, the next slide, is the answer. So what is this one? Safety or liveness? You tell me.
Liveness.
Liveness. Why liveness?
Because eventually you will detect.
Yeah, so eventually is kind of a word, a liveness word, huh? Yeah. So that means if in a given prefix, maybe I have not yet detected it, but I could have, in the extension, I can always detect it. I can always make an extension where I do detect it. So this is a liveness. The good thing will eventually, the good thing is the detection. So that's liveness, yeah. So of course the other one has to be safety, yeah. If our specification is good. If a node is detected, then it has actually crashed. That's very easy to break, yeah? How do you break it? I tell me P1 has crashed, but it has not really crashed, but it's broken, huh? So if I make a mistake here, then I've broken it. So this is safety, yeah? I break the system, okay? So it's very easy to implement in a synchronous system. So let me show you a kind of pseudocode for that first. Very simple. So I'm assuming now the system is synchronous, and I want to implement P. And the synchronous system has a transmission time between 0 and delta seconds. Okay? And every gamma seconds, the node sends a heartbeat message to all other nodes. And every node waits gamma plus delta time units. And if it did not get the heartbeat, then it knows that the node has crashed. Because the maximum time is delta, the delay, plus the time of the periodic detection. So if it waits gamma plus delta, then it's guaranteed that if a message was sent, it will get it. But if it did not get it, then we know for sure that PI has crashed. Okay? Because these are bounds. So that's very easy. Okay? And we can prove the correctness of this. So we have to prove the 2 properties. So this is something you can go through specifically. Yeah? So the strong completeness. Now we have a node that has actually crashed. We have to detect it. So a crashed node will not send a heartbeat. And if you look at the code, you will see that every node will notice the absence. That every node will time out and notice it. So that is strong completeness. So what about accuracy? Can there be mistakes? Okay, can it be a mistake? So here we have two nodes here. The maximum time, what is the maximum time between two heartbeats? Well, the first heartbeat might take 0, the message would take 0 time, and the second one takes delta, and the gamma is the time in between the heartbeats. So the maximum time is, here it's minimum, here it's maximum. It's gamma plus delta, okay? That means if the node is alive, then you must receive that. So if you don't receive it, you're guaranteed the node is dead. You must have received it in this interval, okay? And that means that you will not make a mistake, okay? You will not erroneously think that the node is crashed. Okay, so that is the perfect, that's easy. What about the eventually perfect? Now this one is a little bit more subtle, because here we don't know the bounds. Now remember, we don't know. And the interface is more complicated. We have two possible events, suspect and restore. Either it suspects the node to be have crashed, or it says, no, it corrects the mistake. It does not suspect anymore. Okay? And it has two properties. It has strong completeness and eventual strong accuracy. Okay? That means eventually it will not make any more mistakes. Okay? So it's almost the same specification as perfect, except here we have eventual strong accuracy. That means it's allowed to make mistakes for a while, but eventually it won't. Okay, so how to implement this beast? So we're assuming a partially synchronous system. Now, this is very interesting, the reasoning we do. So there will eventually be some bounds, but not in the beginning. Okay? And we assume that every gamma time units, the node will send a heartbeat, as before. So there's like a loop, timeout loop, sends the heartbeat, waits, gamma, sends heartbeat. Okay. Now each node will wait at some number, let's say t, big T, time units, and it thinks that that's the time it will get the message. If it did not get a heartbeat in this interval, it will suspect the node. Okay? And it puts it in a suspected set. And if it does get a heartbeat, and the node is suspected, then it says, I've made a mistake. I indicate restore, I remove from suspected, and I increase t. So that's the algorithm. So you wait t starts out being some small number, so that means you're suspecting the nodes a lot. But you will eventually get the heartbeats, so you correct your mistakes. But you keep increasing t, until t is bigger than the bounds. Okay, so let's see how that works. There's actually multiple conditions. Okay. Okay. There's actually two things that have to happen. So let's say I suspect P by Q. Q suspects P, but it's an incorrect, so it receives the heartbeat and increases the timeout. So the timeout keeps increasing. Now two things happen now. Eventually the system becomes synchronous, which means there's a bound on the message travel time. Okay? And eventually t becomes larger because t keeps increasing than this bound. So there's a bound. Once the bound exists, t keeps increasing. Eventually t will become larger than that bound. And at that point, Q will never suspect P again. You see? Two things have to happen. First of all, the system has to become synchronous. That means there is a bound. Before that, there's no bound, and the time could be any weird numbers, big numbers. But eventually it becomes synchronous. So there is a bound, and T keeps growing. And then some later time, T will get bigger than that bound, okay? Larger than the unknown bound, so it's basically larger than gamma plus delta. Gamma is the time between the sending of the heartbeat, and delta is the message travel time. So eventually t is bigger than gamma plus delta, and at that point, Q will never suspect P again, because the message will always arrive before T, before the end of the T interval. You see that? You see that there's these two conditions, that you see how somehow we're handling the partially synchronous idea, that eventually there's a bound. So that's the first thing. There is a bound, but we don't know it yet. But there is a bound. And T keeps increasing, and then there's a second point when it becomes bigger than that unknown bound, which exists now. You see how there's two things going on here? The bound existing, but we still don't know it, and T becomes bigger than that unknown bound. And the point is, if P is correct, then Q will always receive the heartbeat, and it will no longer make any mistakes after that time. You see that? So this algorithm works for a partially synchronous system. You see that? You see how it's working, huh? So I'm in a loop, I'm sending heartbeats, and then I wait. So every gamma I send a heartbeat, and I wait T. So the gamma never changes, huh? I send periodic heartbeats, and I wait the time T. Okay? And if I don't get the heartbeat, then T is too small. And then I do get the heartbeat, I increase T, and I keep increasing T. So that's the point. T keeps increasing, but the question is will it increase enough? Well, assume that we have to have some condition on how T increases. T should not have a limit. T should increase by some amount so that there's no bound on what T will be. So if T has some finite limit, it's not going to work. But if we add something to T, or if we multiply T by some number, then it's going to work. Okay? Because T does not have a bound. So you see the two conditions. It's important to understand that there's the two conditions. Okay. Okay, so then, now you've seen P and eventually P. Now I have to say something about the course. For a big part of the rest of the course will be organized like this. So the slogan, from P to eventually P. So the idea is we start by making an algorithm, that works in the case of perfect failure detector. That's usually kind of easy because the perfect failure detector is very strong, never makes mistakes. And then we try to extend it for eventually P. Sometimes that will work. Sometimes it will work. Sometimes the same algorithm works for eventually P, but sometimes it will not work. Sometimes, okay, it works. Sometimes we will need new ideas to make it work. So when we're going to do this for consensus, for example. So consensus is very easy when you have P, okay? All the correct nodes, you just take it, they all know, everybody knows who has crashed. So you just make a deterministic decision, and that's easy. How do you extend that for eventually P? Because you don't really know when the nodes have crashed. So you need some new ideas, and the new idea will be something called majority quorum. Okay, that's what we'll see later. So we will have some new ideas that will allow us to get around the fact that we don't really know for sure whether the nodes have crashed. Okay? So this is kind of how we're going to organize it. and you will get better and better idea on this eventually P thing, okay? So eventually P is a very important concept in distributed algorithms, okay? Okay, so let me stop here.